Okay. So, I think we can start. So, in the last lecture we started discussing about priors and how to model priors, and we did discuss about conjugate prior in details kind of, and then we were discussing about exponential family. We saw that how Gaussian distribution comes under the exponential family. That is one example that we did solve, and I told you that please look into the fact that how other popular distribution comes under exponential family, because that will be in the homework. There will be some problem where you have to show, for example, let us say how binomial distribution falls under the exponential family, and if it does, what are the parameters, what is c theta, what is eta x, what is t theta, what is r x, so all those things, right. And then one statement that I made was that mixture of conjugate prior is also conjugate, and in that context we were solving one problem which we did not complete. So, today we will first complete that problem, where the coin tossing example, right, where we will first see that how in this case mixture of conjugate prior comes out to be a conjugate and how to find it out actually. And then we will proceed with other things such as hierarchical base we are supposed to discuss, we did not discuss, empirical base we are supposed to discuss, we did not discuss last time, and also non-informative prior we will talk about that. Okay. Non-informative prior actually we will do first, but we will go very quickly over this, because we will not use this we will not be using non-informative prior in this course, and therefore, we will not go into non-informative priors in much details. I will just tell you what it is and how it is computed, and that is all, but I will not prove the properties, I will just state the property. Okay. So, with that let us start, and let us start with the exact example that we were solving last time, right. So, if you remember, the example that we were solving was the coin tossing example. That is the only example we have been solving till now, but there was a catch in the example. The statement was that there is a coin, I have tossed the coin n times and I have observed n1 heads and n0 tails. This was the data that was given to us. So, it was not a proper data where you know what you obtained first time, what you obtained second time, but rather it was a data which was only concerned with the count of heads and the count of tails. And that is why I told you last time also that this will not be a Bernoulli distribution, the likelihood, it will be a binomial distribution, because we are only concerned about number of heads rather than getting a head first time, getting a tail second time, and something like that. Okay. So, that was one catch here. So, let us start from the beginning actually. So, we toss a coin n times and obtain n1 heads and n0 tails. Okay. And because of this problem statement, where we are only concerned about the number of heads and tails we are getting, the likelihood is going to be binomial. Okay. So, the likelihood is binomial. Okay. The likelihood is binomial because of the problem statement. So, now we want to solve the Bayesian inference, we will want to find our probability of theta given d. So, our objective remains the same, we want to find the posterior distribution of theta. So, that is probability of theta given d. So, we want to compute probability of theta given d, where theta is the parameter of my distribution, right. Theta is the parameter of my distribution which I want to infer once I have the data. Now, how do you compute a quantity like this? How do you do Bayesian inference? What is the first step? You will assume a prior, Bayes law, as I said last time, right. So, the thing is that you will assume a prior, and if you remember, for this we assumed a prior to be mixture of beta distribution, because binomial the conjugate prior is beta, and we took the prior to be mixture of beta distribution. So, we consider p theta, which is my prior, to be 0.5 beta distribution with parameter 20, 20 plus 0.5 beta distribution with parameter 10, 10. Okay. And if you remember, I said that this one of this component corresponds to, in a soft manner, corresponds to the coin being unbiased. So, it will peak around 0.5 and then be symmetric. The other one corresponds to it is biased towards head. So, it will be towards, the mean will be around 0.85 or something like that. I mean, not the exact number, but something like that. Okay. And now, remember I also said one thing last time, that this 0.5 is like a indicator variable. So, it is more like probability that z will be equal to 1, and this is more like probability z will be equal to 2. Now, why 1 and 2? You can take 0 and 1, it will not matter. Okay. I am taking 1 and 2, but you can take 0 and 1, minus 1 and 1, none of that will actually matter in this case. Okay. So, this is my prior. My likelihood is binomial, which is same as Bernoulli with one additional factor, if you think about it. I mean, at least the form is same. Okay. And so, the question or rather what we will do is, with this setup, the posterior is probability theta given data will be equal to probability z equal to 1 given data beta 20 plus n1 comma 20 plus n naught, and this derivation we have done last lecture, if I am not wrong. Okay. Plus z equal to 2 given data beta, it was 10 I guess. So, 10 plus n1 comma 10 plus n naught. Okay. So, this is what it is supposed to be, and the only bottleneck we have is how to find out probability of z equal to 1 given data and probability of z equal to 2 given data. So, the only bottleneck right now is to find out those two terms. Okay. So, we want to find out in a generic sense probability is equal to probability z equal to k given data. This is what we want to find out, and by using the Bayes law, what we can write here? This will be equal to probability z is equal to k, probability d given z equal to k, and the denominator I said was that I will write it in the expanded form, the original Bayes law, the most popular one, which we rarely use. So, summation over k prime probability z is equal to k prime probability data given z is equal to k prime, right. Now, with this setup, what is probability z equal to k in the numerator? Probability z equal to k, what is that value when k equal to 1, let us say 0.5, and k equal to 2 also 0.5. How are we getting it? We are getting it because here it is, you see. So, from there you get probability z equal to 1 is equal to 0.5, probability z equal to 2 equal to 0.5. So, those are the terms that are known to us. So, we need not worry about them. What is unknown? Probability d given z equal to k. And until this point is what we did actually last time. What we want to find out is this term, right. So, the question is then with this setup, this one how to compute. Okay. So, this is the thing we would like to compute. So, how to compute probability d given z equal to k. Okay. So, this is the term that we will like to compute. Okay. So, now we want to compute probability d. Okay. So, now we know, okay, let me give some equation numbers. So, maybe I will give this one as equation number 1, this one here as equation number 2, this one as equation number 3. Okay.
So, which is
1 is the prior. Okay. So, 2 is actually theta given d, that one, the posterior is 2, okay, and 3 is basically the Bayes law that I used. Okay. So, from 2, okay, we know from equation 2, what do we know? Probability of theta given d comma z equal to 1. So, from 2, can you tell me what is this equal to? What I want to find out is theta given d, the data, but I am telling you that z is equal to 1. That is the additional information I am giving. What will be this equal to from this equation number 2? See, I have told you that z is equal to 1. So, that means the second term will become 0. So, only the first beta component will be there, because since I have given you z equal to 1, probability z equal to 1 given data will become 1. Probability z equal to 2 given data will become 0, because I am telling you z equal to 1. So, you will end up getting beta 20 plus n1 comma 20 plus n2. Clear what is happening? When you give something, that is observed. So, that means that has happened. I am telling you z equal to 1 has happened. So, that means that component becomes 1 and anything else will become 0, and then you will get what I just said. Okay. So, this is equal to beta, I think 20 plus n1 comma 20 plus n0. Okay. Now, I will like to generalize it to, so in generalized form, see if you can follow it or not, it should be form probability theta given data comma z is equal to k. So, k can be either 1 or 2 in our case, but if there are 3 components, k can be 1, 2, 3. If I have 10 components, k can be any number between 1 and 10, right, any integer between 1 and 10. So, this is equal to beta. Now, this 20 is nothing but your prior component corresponding to z equal to 1, right. So, that is A, our notation is A. So, I will call it AK plus N1 comma BK plus N0. So, when k is equal to 1, my AK is equal to 20, BK is also equal to 20. When k equal to 2, my AK is equal to 10, BK is also equal to 10, that you get from equation number 2. From equation number 2 you get that, right. So, this is a generalized form. I wrote it because ultimately we have to find it out for both k equal to 1 and 2. So, let us do it in a generalized form. So, okay. So, remember this. So, now, so I will call it what, equation number 4, we will need it later. using Bayes' law on LHS of equation 4. Probability theta given d comma z equal to k will be equal to, what will be there at the numerator? I am using Bayes' law. So, this is my posterior in some sense. Okay. So, what will be the first term? So, assume z equal to k is not there, just assume that. Then what would be the first term? Probability of theta, the prior. Now, z equal to k is there, so it will be theta given z equal to k. So, probability theta given z is equal to k. Okay. The second term would have been equal to k. But remember, once theta is given, d is completely defined. You do not need care about z, because that is the relation between data and theta. Z is a prior parameter, so that has no consequence on the likelihood. So, that will be a conditional independent. So, probability of d given theta would have been the normal thing, and along with that you get this, but this anyways will become turns out to be conditionally independent, because it is the data we are talking about. Z is a parameter of the prior, your likelihood do not have any z. So, that will not matter. So, we will write it down like that, and the denominator will be probability of d given z is equal to k. And isn't the denominator that is our bottleneck, that is what we want to find out. So, I am going to use this expression to find out the denominator actually, because the left hand side I already know from equation 4. The denominator is something we do not know. The other things, what is theta given z equal to k? Theta given z equal to 1 will be equal to 0.5. Theta given z equal to 2 will be 0.5, that is the prior. So, and d given theta will become the likelihood binomial, and the denominator is the unknown. Okay. So, let us write it down actually. So, from equation 1 we know that probability of, what was the first term, theta.
So, what did you say about probability of theta given z equal to k?
It will be equal to the beta, right, beta components. Beta I said 0.5, that was wrong, it will be the beta components, you are right, yeah, will be equal to beta 20 for k equal to 1, and this will be equal to beta 10 for k equal to 2, right. From equation 1, that is what we are getting. Okay, this one I will call equation 5, by the way, I will need it. Okay. Okay.
In P d given theta comma z equal to k,
Yeah.
like will theta not change with value of z? So, depending on that P d given
The both are on the right hand side, that is conditioned. So, when you are conditioning, theta is fixed, whatever is on the right hand side is conditioned. So, once theta is fixed, z will not matter, otherwise you are right, if theta was on the left hand side, then it would have mattered. Okay. So, now given theta, d is conditionally independent of z. Therefore, probability of d given theta comma z is equal to k will be equal to probability of d given theta. Okay. So, once you know the theta, that is all you need for your likelihood. along with the data obviously. You do not need any more parameter. Okay. And this is actually equal to, remember, this is the likelihood which is equal to binomial, by the way. I am not writing it, but remember that it is a binomial distribution. Why binomial? Again, because of our problem statement. We are only counting, we are not having a fixed position. Okay. Okay. So, now if this is clear, so now later we will denote something important here, which you will need later actually in sampling. So, what we will denote is, or what we will introduce is actually the unnormalized distribution, because many times in probabilistic machine learning uncertainty quantification you have to work with unnormalized distribution. Okay. So, we will introduce unnormalized distribution now. So, we represent probability of, what was the first term, theta given z equal to k, I guess, as q theta given z equal to k divided by z naught, okay, where q is my unnormalized distribution. So, it will not integrate to 1, it will integrate to z naught, and then z naught and z naught will cancel out, and then you will get a 1. Okay. So, where z naught is the normalizing constant. And this is my unnormalized distribution. You will realize it, because we want to find out that term. So, that is why. So, this is a trick that we use to find out the unknown term, right. Unnormalized distribution. Okay. So, what we have done is very simple. If it is a Gaussian, I am writing the exponential component only, and 1 by sigma root 2 pi I am saying that is z naught. Think of it like that. That is exactly what we are doing, right. If it is beta, I am writing the numerator, and the denominator is a beta function. For beta, the normalizing constant is beta a comma b, where beta is beta function, not beta distribution. So, I am not writing the beta function now as z naught, and the other thing I am just writing. Okay. So, that is what we are doing here. If it is binomial, NCx or NCn minus NCn1 in our case, that I am 1 by actually, that I am separating out, and the rest of the portion I am writing. Okay. So, we represent this as this. We also represent probability of d given theta as q d given theta by ZL. L stands for likelihood, O stands for not, stands for prior. Okay. And we denote probability of, what was the other term, theta given d comma z equal to k, theta given d comma z is equal to k. This I will denote as q theta given d comma z is equal to k divided by z n. What is the number n denoting? I have performed n experiments. That after n experiments, what is that thing? Okay. So, the number n, or the n is denoting, because you remember I said I toss the coin n times, I get n1 heads and n naught tails. So, this n is denoting that I toss the coin n times. So, that is my data. Clear? We do one more thing. Okay. And the thing that we do is that if I, now the last term, right, I can write it as product of the other two term proportional to, right. So, what we do here is that we also assume q theta given d is equal to q theta given z equal to k q d given theta. Okay. That the unnormalized ones, if you do a product, you will get it. I am saying we assume, but actually you can prove it, it will hold, okay, because it is a joint distribution. Okay. Okay. So, now with this setup we return, and we return where? We return to this one. Okay. Now, with this, so let me number them. So, 5 is what we have numbered. So, let us call it 6, 7, 8. Okay. So, what I will do is I will take 6, 7 and 8 and substitute it into equation 5. This will be 9, which I will need later. So, substitute 6 to 8 in 5. What was the left hand side? You remember it in 5? Probability of theta given d comma z equal to k. So, that I will write as q theta given d comma z equal to k divided by zn. So, I will get q theta given d z equal to k divided by capital Z. Okay, do not confuse this to z, I just realized. Small z is the indicator variable, capital Z is the normalizing constant. So, do not confuse the two z's. So, Zn is equal to, what do you have in the numerator? The first term, q theta given z equal to k divided by z naught, right. What is the second term? Q d given theta divided by z l, and what is the denominator? The unknown term, probability of d given z equal to k, small z equal to k, right. So, now you see what I did. Now, that numerator terms will cancel out, left hand side, right hand side, using equation 9. So, using equation 9 we will get, let me write here. So, using 9 we get probability of d given z equal to k will be equal to, I think in the numerator you have what, z n I guess, and in the denominator you will have z naught z l, because the q will cancel each other out, right. So, what does it say you? This tells you that you can find out the left hand quantity, assuming you can find out the normalizing constant, which is a big assumption. In general, you will not be able to find them out. Definitely, you will not be able to find out z n in most cases, but in this case you can, because it is conjugate prior and combination of conjugate prior, right. So, each conjugate prior you can find out z n. So, this will work. So, what will be z n, by the way, tell me? Z n will be, what is z n? The normalizing constant of the posterior given for a given k. Okay? For a given k, what is the posterior? Beta distribution, right. What is the normalizing constant of beta distribution? Beta function. So, the numerator will be beta, let us say in our case 20 plus n 1 comma 20 plus n naught. For our case that will be our z n. I will repeat this part again. What is z n? From here you see, z n is the normalizing constant for probability of theta given d comma z equal to k. What is probability of theta given d comma z equal to k? That if I go back, I have it somewhere here, and I can see that it is a beta distribution. equation number 2, right. And normalizing constant of the beta distribution is beta function. So, Zn will be equal to beta function, clear. So, Zn will be, so for our problem, for our case, Zn will be equal to a beta function. Now, I have already used capital BETA for beta distribution. So, I will write it in small b, okay. Beta, you have what, 20 plus n1 comma 20 plus n naught, okay, for our case again, okay.
Sir, equation number 9, can't we write it in terms of P, the actual P?
No, then there has to be a normalizing constant, otherwise it is a joint distribution.
There will be the issue of normalizing constant for
Yeah,
writing it in
yeah,
terms of P.
because then it will not hold, because then it is the product law, but it is the base law, right. What I am writing is the base law. So, where is the denominator? For writing it in terms of that, I will need the denominator, which I am ignoring here, because I am cancelling it out. Yes. Okay. So, Zn will come out, okay. Zn will look something like this. Okay. Obviously, I am assuming k equal to 1 here, that is why. For k equal to 1, for our case with k equal to 1, obviously I have to write, otherwise this will not hold. What will be Z naught? Beta function with 2020. Z naught will be the prior, for k equal to 1 it is beta 2020. So, it will be beta function with 2020. So, the notation I am using here is to be carefully followed. When in the beta, when I am writing B as capital, that means distribution. In the beta, when I am writing B as small, then it is function. Okay. So, B capital ETA is distribution, B non capital ETA is function. Okay. So, Z naught will come out to be beta 2020, clear. What will be ZL? 1 by NC N1, because it is the head I am talking about. So, 1 by NC N1. Okay. So, ZL will be C N1. So, just substitute this and you will find out what you want. Okay. What is the binomial distribution formula? NCx p to the power x q to the power n minus x. So, if you do p to the power x q to the power n minus n and integrate out, you will get 1 by, that has to cancel out, because I have written q by z and there it is already in the product form. Okay. So, that is why. Okay. So, the idea is you can do things analytically if your prior is mixture of conjugate prior, that is the whole message. I did this to show you, but remember the message. The message is simple, and that we discussed last time, that if my prior is modeled as a mixture of conjugate prior, still you can do things analytically. Clear? The message is clear. This problem you can always check out. Anyways, the exact values are given in the slides later. If you check it out, I think it comes out to a 0.6 and 0.3, these two terms. Okay. But the message is clear, is more important, which is that mixture of conjugate product is also a conjugate product. Okay. That is the main thing. So, the main take home message here is that mixture of conjugate prior is also conjugate. Okay. So, this is the main message. problems you might be able to solve, you might not be able to solve, but they are solvable if it is conjugate prior. But this message should be absolutely clear. Okay. Any doubt, any question on this part? Because otherwise we will start with the next part, which is non-informative prior. This was actually pending from last lecture, right. So, then let us start with non-informative prior. Okay. As I said, I will not go into details. So, the next thing we want to talk about, or we want to at least touch upon, is non-informative prior. Okay. What is the non-informative prior? A prior that does not influence the posterior. So, it is only the data that will control the posterior. Okay. So, it is by definition or by the name itself you can say a prior that does not influence the posterior. Okay. That is by definition non-informative prior. But along with that there is one more criteria actually, which is this should be invariant under any transformation. Remember probability transformation, determinant of the Jacobian for multivariate case, or the determinant of the not determinant, I mean the absolute value in the scalar case. So, that probability transformation we covered. So, for a non-informative prior, it should also be invariant under probability transformation. Why is it important? Because if it is non invariant, then you do a transformation, it will become informative prior. So, if something is really non-informative, you do any transformation on this, it should still be informative. Okay. So, the other condition is that it should be invariant to probability distribution. Okay. And actually Jeffrey's non-informative prior, actually this condition was given by Jeffrey, because he is the one who defined what is a non-informative prior, and Jeffrey's non-informative prior satisfies both the criteria. Okay. And we will see that. But before that, let us revisit the example we did earlier, coin tossing example. Remember for beta 1 comma 1, what was we getting? Our theta map was becoming equal to theta MLE. In second lecture I guess, no, the third lecture maybe, third lecture. So, remember the coin tossing example for beta 1 comma 1, we obtained, this was in lecture 3. Okay. If you do not remember, please check out lecture 3, we did this. Okay. We obtained that theta map was equal to theta MLE. But remember I said that although and it might seem non-informative from a map point of view, because the effect of prior is not getting visible in the map, and so map and MLE are become identical, but it is not a non-informative prior. And why was it not a non-informative prior? Can you remind me? We found out the posterior, which came out to be the expectation, and we got the result to be NH plus 1 by N plus 2. So, the posterior is getting influenced by this. Okay. So, however, this is not a non-informative prior, as probability of x tilde equal to 1, which is that you have tossed the coin 10 times, you what is the probability you will get a head on the 11th time, right. In the next toss, what is the probability you will get a head? Given data, this came out to be n plus 1, sorry, nh plus 1 divided by n plus 2, right, because alpha divided by alpha plus beta, and alpha was coming out to be nh plus 1 comma nt plus 1, beta was coming out to be nt plus 1, alpha was coming out to be nh plus 1. Remember this thing? So, lecture 3, if you do not remember, go and check out lecture 3, this was derived. Okay. So, now with this setup, what do you think will be a non-informative prior? One option obviously is that if this 1 and 2 vanishes, then it should be, because then it is the MLE result. How can 1 and 2 vanish? If A equal to B equal to 0, but that is undefined, beta is not defined as at A equal to B equal to 0. So, it is in the limiting condition, limit C tends to 0, beta C comma C. So, with limit C tends to 0, beta C comma C as prior, we obtain probability of x tilde given D is equal to nh given n, x tilde equal to 1 actually. Okay. However, there is a catch here. Okay. Obtain this as long as you will only obtain this result as long as you have at least one head and one tail in your data. Okay. You will only obtain this as long as you have one head and one tail in your data. I will explain why that is the case very quickly with the beta distribution. Everything is coming from the beta distribution. Okay. So, let us take the beta distribution and let us try to understand what is happening. So, beta A comma B is only defined for A comma B greater than 0. Okay. If A and B are equal to 0, this is not, this is a function that is not defined. Okay. And why is it not defined? This distribution, actually this distribution is defined, but we call it a improper distribution. So, to be more particular,
sir, when we took beta 1 earlier, so the posterior distribution was coming to be nh plus a minus 1. So, if we put a equal to 1 there, so the posterior distribution will be the same as earlier, like there is no influence of the prior distribution.
wrong.
Sir,
Yeah, so I will tell you that. So, you are right, the posterior distribution was not coming out to be nh plus a minus 1, it was coming out to be nh plus a, that minus 1 is coming from the beta distribution, because beta the form is the theta to the power a minus 1, 1 minus theta to the power b minus 1. So, beta a comma b is equal to theta to the power a minus 1 and 1 minus theta to the power b minus 1. So, that minus 1 is there even when the parameters are a and b.
so, sir, if we put a equal to 1, b equal to
If you want put a equal to 1, b equal to 1, you will get beta 1 1, right, which is equal to theta to the power 0 and 1 minus theta to the power 0.
So, can we say that
but that is not the posterior.
So, but
That is not the posterior. The posterior you are getting is NH plus A and NT plus B.
sir, but it was
The distribution form is theta to the power NH plus A minus 1 minus theta to the power NT plus B minus 1. That is the distribution form. But the parameters are minus 1 is supposed to be there in the form itself. So, the parameters are NH plus A and NT plus B. So, I am talking about the parameters here. I am not writing down the distribution if you look carefully. I am writing that my distribution is here what? This NH plus 1, this I am getting how? Through the predictive distribution. So, what is the distribution here? The distribution here is coming out to be NH plus A minus 1. A is equal to 1. So, NH plus 1 minus 1, but your parameter is NH plus 1 and the mean of that is A by A plus B. What is your A now? NH plus 1. What is your B? NT plus 1. NH plus NT is equal to N. So, that minus 1 is still there in the expanded form. When you write the function, the minus 1 is there, but though the minus 1 is not included in the parameter. Okay. So, to be more particular, limit c tends to 0 beta c comma c is a improper prior. Okay. A improper prior means it is a prior, a valid prior in most cases, but you cannot normalize it. Why can't you normalize it? Because your normalizing constant will become beta minus 1 comma minus 1. The beta function for minus 1 does not exist. The beta function only exists up to 1, 0. And because as C was correctly pointing out that there is a minus 1. So, with 0 and 0 you will get beta minus 1 comma minus 1 and that is undefined. Okay. So, in the limiting condition also this is an improper prior, which means this you can write down the expression theta to the power minus 1 is a valid thing, but in denominator you cannot find out. So, it is unnormalized. Okay. Improper prior means unnormalized. Okay. And there is no problem with using improper prior as long as your posterior has to be proper. So, you can use an improper prior, but you are interested in the posterior. So, if after observing data your posterior is getting proper, then it is fine. So, there is no problem with using improper prior. The condition is once you have observed data, it should become proper, because otherwise the posterior will be undefined, and posterior you definitely need in distribution form. Prior is what you are assuming, posterior is what you are interested in. Okay. So, we can use improper prior as long as the posterior is proper. Okay. Clear? And now, for your posterior to be proper, you will need both A and B to be greater than, not A and B, you will want your posterior distribution parameters to be greater than 0. Okay. So, that means in coin tossing example, we have probability of theta given d as a beta distribution with A plus NH comma B plus NT, right. So, I can call this as my an and this as my bn, the posterior parameters, right. Now, when will an and bn be proper? When will an and bn be greater than 0, given that a and b are tending towards 0? When will that happen? Only when you have observed at least one head and one tail. At least, so that is the statement I made earlier, that this posterior predictive distribution will only give you result only when you have observed at least one head and one tail. Otherwise, your posterior itself is undefined, so you do not have a predictive distribution to start with. So, this result nh by n will not be valid. Clear what is happening? So, all of this is coming from the property of beta distribution. Because my posterior is beta, an and bn has to be greater than 0. Now, I have taken an improper prior, so a and b are as good as 0, limit towards 0, right. So, now if I need an and bn to be greater than 0, I need at least one head and one tail, nh should be 1 and nt should be 1. Even if one of them is 0, you are in trouble. Clear? What is happening? So, therefore, given a comma b tends towards 0, we need nh greater than equal to 1, and remember nh is a integer number of heads, it cannot be 1.5, 0.5, you have either observed not observed. We need nh greater than 1 and greater than equal to and nt greater than equal to 1. Okay. For an comma bn to be greater than 0. Okay. And only then your posterior will be proper. So, you can use an improper prior, but the posterior will become proper only if you have observed at least one head and one tail. And this prior has a name, by the way, this prior is known as Haldane's prior. Beta 00, beta cc is known as Haldane's prior. Okay. So, limit c tends to 0, beta cc is known as Haldane prior. Check the spelling from the slide where I have typed it, this spelling might be wrong. Okay. I mean A or E, I am a little confused. Okay. But even with this, this is not a non-informative prior. Why? Because the other condition was it has to be invariant against transformation. So, the actual non-informative prior you can prove it is equal to half comma half. Okay. We will not do that, you try it out, I will give it in the homework for you to prove. Okay. That so that beta half comma half is a improper, is a non-informative prior, that will be a one homework question. So, you prove it, I am not proving it. Okay. But beta half comma half is a non-informative prior, this is not, because it is not invariant to transformation. Okay. Although the first condition is satisfied, it is the posterior is not affected by it. Okay. Okay. So, the last thing in non-informative prior is the Jeffrey's non-informative prior. The person who came up with the definition, we should at least look into his prior. Okay. Jeffrey's non-informative prior. So, by the way, in the slides there is also translation invariant prior that I have included. It is very simple, look into it on your own. Okay. If you have doubt, you can come to me, but in the slides later you will get it. Okay. Jeffrey's non-informative prior. So, this Jeffrey, what he did was that he was trying to find a prior which is non-informative, which means the effect of the prior will not be there and the posterior will only be governed by the data. But he also wanted it to be transformation invariant, so that if it is non-informative, any transformation should not make it informative. Okay. And in that he used information theory to come up with this prior, and that makes perfect sense to me at least, because the prior should not convey any information. So, how do you find it? By using information theory.
Sir, if the pair is not giving any information, then why?
Correct. Two cases, because Bayesian, one of the main advantages is, you are right, the prior information you can incorporate, but even without that, Bayesian is robust in the sense that it is prone to less prone to overfitting and all those things. So, you can, by using non-informative prior, you are only taking decision based on the likelihood, that is true, but it is not overfitting now. Okay. And also objectivity is another criteria. You might need some applications where you want to test two models or something like that, and you will not want your prior to influence those. So, you want objectivity where your objectivity is defined by the effect of data only. So, in that case also you can use it. Neither of this is our objective, so we will not do this in this course, but if you are interested, that those are the two reasons. Okay. And these are actually mentioned in the type slides also in a proper manner, you can have a look. Okay. So, Jeffrey's non-informative prior, this is defined using information metric I theta. Okay. And how do you define I theta? I theta is defined as expectation x given theta del log f x given theta del theta del log f x given theta transpose del theta. Okay. So, this is known as information criteria. What is f x given theta? The probability distribution of x given theta, that is the likelihood. Okay. F x given theta is the likelihood. Okay. X is your data. And does it make sense? It is information theory based, or how is it information? It is basically capturing the gradient of your likelihood with respect to theta. So, change in theta, how will it change the likelihood, the probability? So, that is like an information, right? The effect of, it is the sensitivity of the likelihood with respect to theta. Okay. So, this is known as information metric or information criteria, and the prior, Jeffrey's prior is defined as p theta is proportional to determinant of I theta to the power half. Okay. Now, I will give you some clue why this is invariant against transformation, because you have to remember that the Jacobian is present there, and you take the determinant of the Jacobian. So, that will cancel out and it will become invariant under transformation. Okay. So, you can, again, this will be another question in your homework. I will ask you to prove that, so that this is invariant against transformation. Okay. So, now I have 20 minutes, I will not spend any more time here. This 20 minutes I am going to talk about hierarchical base, empirical base, and one example. I will like to spend more time on the example and less time on the hierarchical base and empirical base. The example is on hierarchical and empirical base. Okay. And with that I want to wrap up prior today. Next class we start machine learning, linear regression. Okay. So, okay. So, next, by the way, before that, one thing is important to mention is that for our case we are more interested in not non-informative prior, but rather robust prior. So, what is a robust prior? Robust prior is a prior that is not influenced by outliers. Okay. If your data has an outlier, it should still be robust against that. Okay. So, for a robust prior generally it is the heavy tailed distribution like students see, like the sparsity promoting priors, those are generally found to be robust prior. We will talk about that separately, because but since I am wrapping up the prior part, this is the last thing on prior, because I am going to hierarchical base. So, I think it is important to note that for this course and in general in engineering applications, we are more interested in robust prior and sparse prior as opposed to non-informative prior. Non-informative prior is more needed for those who are in statistician, let us say. So, in those cases it is more needed. Okay. Why did I cover it? Because I thought it should, for a completeness it should be covered. Okay. Clear? So, robust prior, we will talk about that later, I am not writing it now, but if you want you can take note. Okay. So, now we have hierarchical base. Okay. And I talked about it last time, but very vaguely. I talked about it last time, but very vaguely, right. In hierarchical base, we are interested in finding out probability of theta. I mean, I am not talking about hierarchical base, but this is the normal Bayesian that we are aware of, right. This is the normal Bayesian that we are aware of, prior times likelihood. But we know that the prior is again defined by some distribution which have its own parameter, right. So, we know that prior has its own parameters, and that is what we have been seeing till now, beta 1 1, what was 1 and 1, those were the parameters of the prior. What was AB, AK, BK, 20, 20, 10, 10, those were all parameters of the prior. So, prior has its own parameter, right. How to find out those parameters is the question, and in hierarchical base what it suggests is that to have a prior on those parameters as well. So, hierarchical base let us call it HB, assigns prior on the parameters of the prior. Okay. Now, parameters of the prior is known as hyperparameter, and hence the prior will be known as hyperprior. Okay. So, parameters of prior, the name we have defined is known as hyperparameter. So, prior on hyperparameter is known as hyperprior. Okay. Now, with this, how will it look? So, in the normal Bayesian, without any hierarchical base, it is generally equal to probability of theta given eta, probability of d given theta, where this is my hyper parameter and this is Bayesian as we have defined till now, right. In hierarchical base, it is probability of eta comma theta given data is proportional to probability of eta, probability of theta given eta, probability of data given theta. Okay. And this is the hierarchical base. Now, the obvious question is that eta probability of eta should also have its parameter. So, why are you not considering them? You can, that will be level 2 hierarchical base. You keep on doing, you can go up to level k hierarchical base, no one is stopping you, you can, but we are not doing that. The idea is that you can go as long as you want. But the question is that what is the advantage here? Even with level 1, the basic hierarchical base, are we getting any advantage? Yes, we are, because what is theta? Parameters of your machine learning model. If you think about Chat GPT, just as an example, or GPT-4, how many parameters are there in that model? Trillions is the order. So, the prior will be in the trillion dimension. So, that is a high dimensional space. So, generally your prior is in the high dimensional space, but your hyper prior is generally in a low dimensional space, because you can assume those thetas to all come from a same hyper prior defined by one parameter. They will still be different, but they will be sharing information, because they are coming from the same distribution now, hyper prior is same, but because it is random they will be different, but they will be sharing information, and that helps. So, the idea is that generally theta is high dimensional, whereas eta is low dimensional. And if this is the case, then hierarchical base is useful. If this is not the case, then the utility is less. Okay? If this is the case, HB is in business. Okay. Clear? Not clear? So, let me give you one intuition actually. Think of a mountain. Okay. So, mountain or pyramid, it goes up like this. So, at the bottom the area is more. So, if you are staying at the bottom, can you see everywhere what is happening? That is like a high dimensional space, it is a circle, let us say. But if you go to the top, there is one parameter, but from the top you can see throughout. So, that is the idea, that with hierarchical base you are going up the pyramid and you are reducing the space, and from there you can actually trace the whole thing. So, that is the intuition of hierarchical base. Okay. So, think of it like a pyramid. With hierarchy you are going from bottom to top. In the bottom, if you are at the one end, you do not know what is happening at the other end, because it is so large. But if you are at top, then you can see that. Okay. So, that is the intuition. Empirical base, okay, is the special case of hierarchical base. Okay. So, often it is possible to integrate out theta to obtain probability of eta given data, right. So, what I am saying is that probability of eta given data is equal to integration over theta probability of theta comma eta given data, right. And you can do it analytically. If you can do it analytically, then EB comes into picture. So, in EB, in empirical base, we use point estimate for probability of eta given data. So, this is approximated as let us say eta bar. So, you approximate this using a point estimate. Okay. So, this is not equal to eta bar, this is wrong actually. I mean mathematically wrong, actual thing is, yeah. So, this is mathematically you write it as a delta function eta bar eta. So, basically the PDF is a delta function which will take 1 when eta equal to eta bar, not 1, I mean infinite delta function, the integration is 1, and for other places it is 0. Okay. So, that is a point estimate. Okay. So, and how do you find out eta bar? Where eta bar, you find it out by maximizing. Probability of eta given d. Okay. So, this is what you do in empirical base. Now, I am going to claim that this is equal to MLE in under certain condition, and we call it level to MLE, and I will show you that how. Okay. So, eta bar I said is equal to arg max eta probability of eta given d, which is equal to, I am only writing the probability parts, or okay, let me write it, arg max eta, what is this equal to? Integration of theta, probability theta comma eta given data, right, and then you use the law that I, or the Bayes law that I wrote earlier, arg max eta integration over theta, you will get probability of eta, probability of theta given eta, probability of d given theta, d theta. Okay. Now, remember I said that eta is generally low dimensional, and because eta is low dimensional, it is less prone to overfitting, and because it is less prone to overfitting, one common choice for probability of eta is equal to uniform. Okay. So, eta low dimensional and hence less prone to overfitting, and therefore, eta generally can be assumed to be uniform, okay, in which case it will become constant, right. So, if it is constant, then what will happen to the above equation? With this, eta bar is equal to arg max eta integration theta probability of theta given eta probability of d given theta d theta. Now, you tell me what is this quantity inside the integration, the total thing. What is this? Theta times d, what will it give? D given eta, d comma theta given eta is what is inside the integration. Isn't it probability of d comma theta given eta, right, from the product rule, and then what will happen because of the integration? This will be equal to theta will vanish, marginalization, you will get d given eta, which is known as the marginal likelihood. So, you are maximizing the marginal likelihood, d given theta is the likelihood, d given eta is the marginal likelihood. So, you are maximizing the marginal likelihood, that is why it is type 2 MLE. So, this is equal to probability of d given eta. So, this is known as the marginal likelihood. Okay. So, that is why this is known as the type 2 MLE. Empirical base is type 2 MLE. What will be a type 2 map? Someone from you, I want to answer.
Type 2
Map.
So एक और priority.
Just don't take eta to be uniform. Take eta to be something else. So in that case, probability of eta will remain, and you will end up getting probability of eta given theta. So if you take probability of eta to be non-uniform, then that term will remain inside the bracket, inside the integral. So this now will become d given eta multiplied by eta, which will give you eta given theta, which is the type 2 map. Okay. So in the slides I have given a table kind of thing nicely showing type 1, type 2, full base and all those things. So you can have a check it out. Okay. So those are there in the slides. Now how much time do I have? 1 minute. Okay. So okay, I will do it next time then 1 minute. I will need 10 minutes for this example, because I don't need to write anything, but it is an example I really want you to understand, to get a feel of where this thing is used and how this is helpful. Okay. So that is anyways there at the end of the slide, but I will do it next time for 10 minutes and then start with the linear regression. Okay. We are done with prior, we will start the linear regression. So the actual machine learning starts now. We will not have a probability of head to estimate, we will have many parameters to estimate now. Okay. And so we will start with that next Monday. If I am not wrong, check it out, I think next Tuesday is also working day. So we have Monday and Tuesday class. So hopefully we will finish up linear regression in those 2 lectures, Bayesian linear regression. Okay. And please review linear regression before coming to next lecture. I will not review linear regression, the frequent is the deterministic one. I will directly start Bayesian linear regression. Okay. So if you want to review, you will please review your linear regression concepts before coming to the next lecture. So next lecture, first we will do the one example, I will show you the results also, that is there, and then we will start Bayesian linear regression. I will need 2 lectures for that, so hopefully by Tuesday we will be done with that. Okay. Thank you.